Hello, everyone. I'm Giuseppe. I'm a cryptographer from Zircuit. And today I want to share with you our efforts on how we accelerated our prover using GPUs. Okay, so it is well understood and well known that computing zero-knowledge proofs is an expensive task. Okay? And this, of course, has an impact on their adoptions, on zero-knowledge proofs adoptions, and usability by users. And any algorithmic speed-ups on the underlying cryptographic primitives employed by these proof systems, of course, will have a huge impact on the overall computation cost, the hardware requirements, and as a consequence, the usability and adoption. What we did actually, is to accelerate the Halo 2 proving system when used in combination with the KZG proving commitment scheme. And this will be the focus of today. So, when you want to accelerate a prover, what you do? So the first thing we did is essentially to profile an execution, a full run of our prover. And you can see on the left side the full running, and in red, one of the main bottlenecks of our prover. And I just highlighted some that will be the focus of this talk, which is, for example, running entity, a number theoretic transform, is like the equivalent of fast Fourier transform over finite fields. The MSM, so the multiscalar multiplication, which are some operations over elliptic curves, and also evaluate Castanet-Gates evaluation, so we will take later a bit more. So once we profiled, we were trying to identify which of these primitives are GPU friendly, or anyway, admit a parallel algorithm for their execution. So I identified, essentially, we were lucky because this corresponds to some of the bottlenecks of our prover. We identified for now 3, so MSM, entity, and Castanet-Gates evaluation. And where, for example, in the multiscalar multiplication, the most known parallel algorithm for it is the Pippinger algorithm. And there we exploit the fact that it uses a parallel bucketing method to reduce the cost of elliptic curve operations. For entities, this parallel algorithm, the multi-radix in particular, exploits the butterfly structure of the entity transform that you can see here on the right. And instead, as regards Castanet-Gates evaluation, what we did, or what we can exploit, is the fact that we need to evaluate a lot of over multiple inputs, thousands of inputs, the same multivariate polynomial. So we can just run this in parallel. So we will see by each of one of these what we did and how we implemented them on GPU. So we start from MSM. We took advantage of Ingonyama iCycle library, so they have great implementation for MSM. And also we tried to use as many optimization as they implemented in their APIs, which mainly we cached. We took advantage of caching the KZG parameters, and the Lagrange basis is like a transform of these, the main KZG parameters. And we did this to avoid copying back and forth to GPU the data. These parameters are used to commit to polynomials, both in a normal form and evaluation form. Also, we took advantage of another feature of the MSM iCycle, which is the precomputation factor, the PCF. So we like benchmark, we found the optimal PCF for our circuit that we will describe later. And this again avoids, is a memory computation trade-off, and we pay a bit more memory to actually reduce the computational cost of performing large MSMs. And another thing we did is like to go through a quite substantial refactor of the Halo 2 code base. This is because we wanted to collect as many independent MSM as possible for 2 purposes. First is to spread the computation over multiple GPUs. And secondly, because we wanted to take advantage of another feature of iCycle, which is the batch MSM. For entity and inverse entity, we did something similar. So again, we used the cycle library, the mixed radix algorithm in particular. We cache fast twiddles, which are some constants, some values that are used in the entity transform. So once those are cached, we just accelerate entities for different sizes. And as for MSM, we collected independent entity, inverse entity, so that we can spread them over multiple GPUs, and we can use batch FFT. The third point is about custom gates evaluation. This is a joint effort with our partner, Maya ZK. And so again, this super secret, which is our main target for this talk, this custom gates evaluation is one of the major bottlenecks, okay? And what they are. So essentially, they are multivariate polynomials that we need to evaluate, and we need to evaluate them over thousands of different inputs, but it's always the same polynomial. These inputs came from the proof table, so if you are familiar a bit with the internal working of LHU, all the inputs and the intermediate values are collected in a big table, which is split in different column types, so advice, instances, fixed, lookups, and others. And a custom gate essentially constrains values in this proof table. And we can think of as a polynomial, so it's there on the bottom, where, for example, we constrain some row value from advice column, multiplied by some instance value, plus some fixed values, minus a constant. This has to be 0. So we need to evaluate this constraint over all the rows, or most of them are subpart of it. Okay? So the idea is to execute these evaluations over each thread of a GPU. So just send the input there. So we can already see here that to do that, somehow we need to pass the proof table to the GPU, okay? Because the threads need to have available all the inputs to process the computation. But this, on its own, the proof table is about 38 gigabytes, so this is just impossible to do that over a GPU. And so what we did, we developed a circuit analyzer, which essentially determines the minimum number of rows required for a particular custom gates evaluation, custom gates polynomial for supersecret. Why we need to pass multiple rows is because, as I said before, these constraints are not for between contiguous values, but maybe they involve like some values on the first row, some other values on the 300th row, and so on. So we need to pass like a big chunk of the proof table to complete execution, and our tool returns the minimum chunk required. So these already cuts a lot the memory needed for the custom gates evaluation. So the idea is that we copy these chunks to the GPU, and each thread just computes the evaluation of the polynomials. And we also implemented some optimization, which is about using GPU streams, where while we are computing evaluations, we are copying data to GPU, and vice versa, and to this is to cut time. When we did this, we realized another problem. We just set the maximum thread possible, but then we just picked memory usage, and we went out of memory. That's because when we do custom gates evaluation, we need some intermediate values to actually compute the final result. For example, in this equation before, at some point we need to first compute the product, then we have the sum over 4 values, and then we have the result. So we need 4 variables somehow in the naive approach to actually compute this custom gates evaluation. And in the original Halo 2 code, it uses the number of variables that is equal to the input. So it's just maximized. There is no optimization there. So again, we used our internal tool, our analyzer, to detect from a custom gates representation, so the polynomial, let's say, to identify the minimum number of variables needed to actually complete the evaluation. And so we refactored the code to just use this minimum number of variables and just this minimum number of memory allocations. And this, with this optimization, we were able to employ 16,000 threads over a single GPU card and reduce the overall memory from the 68, so 30 plus 38, to only 4 gigabytes of memory. So once we completed this implementation, so we set up a server to test, and we set up an AMD EPYC 9374 and with 8 NVIDIA L4 GPU cards with 24 gigabytes each. So we benchmarked SuperCircuit. SuperCircuit is a circuit from ZK Circuits project, and essentially is used to prove validity of Ethereum blocks. And we fed it with 128 transfer transactions, and we set SuperCircuit with 2 to the 20 rows. So the proof table consists of 2 to the 20 rows. So we benchmarked the CPU-only version, so we are around 30 minutes. Then we enabled the MSM and FFT optimizations, and we already cut 24%. So we went to 22 minutes, 56 seconds. And then with all the optimization we implemented, we just went down to 70 minutes. As next steps, we understood that to bring more primitives in, we definitely need to tackle the problem of memory. Memory management is key. And so, for sure, we want to reduce as much as possible the memory footprint of each of these primitives, and also broaden the usage of GPU streams. This is also to cut time, so to exploit computation time and copy data transfer at the same time. Of course, we want to extend GPU support to different primitives, so mainly polynomial arithmetic, vector operations over GPU, and also use similar techniques to tackle another problem, which is lookup evaluations. And yes, and of course, we want to extend these optimizations to not only, we don't want to target only SuperCircuit, but also other circuits like aggregation circuit, compression, and so on. So to conclude, as I said, addressing computational memory bottlenecks makes proof computation practical, even on, with just few GPUs. And GPU acceleration of MSM, NTT, and custom gates evaluation was significantly reduced the proving time of our prover. And as a future, for the future, we will definitely focus on memory optimization and to bring new primitives to GPU. So thank you, and that's all.
Thank you. Any questions? Please.
Hi, thanks for the talk. In the Halo 2 with KZG, I didn't see you talk about the quotient polynomial computation. How much of the total computation is that? And what are you doing to solve it if it's a bottleneck?
Yeah, so I don't have the exact number of the overall running time, but for sure what I can tell you is that the custom gates evaluation is one step towards that. So we're actually trying to target evaluate H function, if you're familiar with the code base. So the CGE, so the custom gates evaluation is just one part, and now as a next step, we are tackling this. So yes, for sure, that's the goal. Yeah.
Right, makes sense. Thanks.
Okay. Thank you, Giuseppe.
You're welcome.
I hope Icicle can add more values in the future for you.
Thank you so much.
Thank you.